Okay guys, so we are doing weekly contest course 3 of Leetcode, and we have 4 problems. Let's do them very quickly. The first one is pretty much easy. We have minimum average of smallest and largest elements. So we have an array of floating point numbers, averages which is initially empty. We are given an array nums of n integers where n is even. Now repeat the following procedure n by 2 times. Either we remove the smallest element, the min element, and the largest max element from nums. And we have to add min and max by 2 to averages. Okay, and you repeat this n by 2 times, and n is even. Okay, so eventually the array will get empty and all the averages will be get added to the array averages. So you have to print the minimum element in averages. So let me just get a test case so we can check this out. Let's see the first one here. 7834 15. Copy this. Okay, I cannot. Oh, again. Just a sec. We have 7, 8, 3, 4, 15. And we have 13, 4, and 1. Okay, so this is nums. Let's just sort it first so it's easier to understand. 1, 1, 1, 3, 4, 4, 7, 8, 13, and 15, right? 3, 4, 5, 6, 7, 8, 9, 3, 4, 5, 6, 7, 8, 9. What did I do now? There are 2 ones. Okay, this is 15, not 1. There's only one. Just right. Okay, let it be. This is just one molecule. Okay. So here we have to take the minimum and the maximum. We'll add these two up and add that number to averages. Then again we'll do the same to this and so on, right? That's how we'll find averages. So we have to print the minimum possible element in averages. So we can just brute force the whole thing, because the time complexity here is, what is n? Okay, and belongs to 2 to 50, so we can easily brute force this solution. So what we can do is just sort the array first, and then we'll keep 2 pointers, one pointer at the first and one pointer at the last, and each time we'll just add the first pointer number at the first pointer and the second pointer and add that to the averages array, and similarly we'll increase the pointer at the first pointer as well as the second pointer until we reach the mid element. Now since n is even, we'll eventually be reaching the mid element like this, where each pointers, the difference between the two pointers is 1, so we'll not have any ambiguity of single element, and after that they will pass each other. So we can just keep 2 pointers, p1 and p2, and we can just add the numbers at p1 and p2 and add that to average, and finally we can just sort this array and take the minimum element. This is the brute force approach. Let's check out the solution here. We have so this is the code here. N equals to nums dot size, and we sort array nums. We keep 2 pointers. The first pointer is 0, second pointer is the last, and we take a double integer answer that is initially equal to maximum of n32, and let's do it while p1 less than equals to 32. So we have this average equals to nums p1 plus nums p2 by 2. We have written it in double because it can also be a double value or a decimal value. That's why we have taken double, and just we have taken our answer equals to minimum of average comments. We don't even need to put it into the average array and sort it. We can just keep taking the maximum. We don't unnecessarily increase the space complexity here, and just increment p1 and decrement p2. So we'll get our answer, and that's accepted. So let's get to the second solution. Okay, so we have, let's see the problem statement first. We are given a 2D binary array grid. Find a rectangle with horizontal and vertical sides with the smallest area such that all the ones in the grid lie inside this rectangle. Now a similar problem we have in question 4, which we'll look at later. That is quite an interesting problem. So this is the mini version of 4's problem. We have a 2D binary array grid, and We have to find a rectangle with horizontal and vertical sides with smallest area such that all the ones in the grid are inside this rectangle. And we have to return the minimum possible area of this rectangle. So this is a very typical problem. Let's look at this. So we have what's the problem? Okay, this is very annoying. Okay, so let us take a look at the problem statement. We have a grid. Let's say we have 1 0 1 1 0 0 and 0 1 0 1 0 and 1. For the moment, let the grid be 2 plus 5 grid. We can take any dimension, so it does not matter. So we have to find the area of minimum area of rectangle, minimum area, such that it covers all the possible ones, right? It covers all the possible ones. So how can we think about it? Since we have to take only one rectangle and we have to take it with the minimum possible area, what we'll do is we'll just look for the vertices, that where should be the vertices of this rectangle, so that it covers all the ones, right? Which means that if this is the whole grid and this is our rectangle, this means okay, this means that this area does not have any ones, right? Okay, and this will be the minimum possible rectangle here. So what can we do here? If you want to find the minimum possible area of such rectangle, we'll have to ensure that no ones lie outside this rectangle, right? And we have to take minimum possible such area. So to maintain such a rectangle, we will take just clear it. Okay. So to maintain such a rectangle, we'll be taking each time we'll be taking the minimum x of all ones. We'll keep track of four things. The first one is minimum of x of all the ones. Second is maximum x of all the ones. The third we have is minimum y of all the ones. All ones. And the fourth is maximum y of all the ones. Sorry for the bad handwriting again. I'm using mouse. So we'll take minimum x of all ones, maximum x of all ones, minimum y of all ones, and maximum y of all ones, where x and y respectively are the row number and column number. Why we are doing this? It's very easy to figure out. If you think a little, you will understand yourselves. Okay. Okay. So why we are doing this? We are doing this because to take the minimum possible area of rectangle, it has to cover all the possible ones, and to cover all the possible ones, you have to take the extreme cases, where the one x is either minimum, and this is x. In our case, In our case, this is x and this is y, right? The row number and the column number. So we'll take the minimum possible x where the ones start coming, the maximum possible x where ones end, the minimum possible y, and the maximum possible y. And using all these four, we'll be able to calculate the minimum possible value of rectangle. So here's the code. Just a quick look. So we have n equals to grid dot size and n equals to grid 0 dot size. That is the respective uh, number of rows and number of columns here. We initially start with x as x is -1, y is -1, x2 as 10,000 and y2 as 10,000. Just to remind you the constraints here, we have okay. So n and n both are between 1,000. So I have taken maximum value 10,000 so that I can take the minimum later. And similarly for taking the minimum, I take the minimum value -1 since the minimum possible value that is less than the possible rows number or column number, it can be -1. So we will just iterate through the grid for I equals to 1 to n, for j equals to 1 to 0 to n, and if that grid I j equals to 1, then we've just taken x1 is maximum, x2 is minimum, y1 is maximum, and y2 is minimum. And if any of them is -1, like if we didn't find any ones here, we'll just return 0 because we don't need a rectangle here, all the numbers are 0. And in the other case, we will just take maximum x minus minimum x plus 1 times maximum y minus minimum y plus 1. This plus 1 we are doing just to make the dimensions fit. Like, it's easy to figure out if we have numbers from 1, 2, 3, 4, and 5, and we have to include numbers from 1 to 5, and number of numbers between 1 to 5. The number of numbers between 1 to 5, there will be 5 minus 1 plus 1. So that's how we'll calculate. That's why we have done this minus. That's why we have done this plus 1. Okay. So proceeding on to the next problem. Okay. So let's read the problem statement here. We are given an integer array nums with length n. The cost of subarray nums L to R is defined as cost L to R equals to nums L minus nums L plus 1 plus dot dot up to nums R, that is the alternating sum of LR. Now our task is to split nums into subarrays such that the total cost of the subarrays is maximized, ensuring each element belongs to exactly one subarray. Okay, so we'll just this is just defining how we are splitting, that I will explain to you. And we have to return the integer denoting the maximum total cost of the subarrays after splitting the array optimally. Okay. Note, if nums is not split into subarrays, like k is equals to 1, the total cost is simply cost 0 to n minus 1. Okay. So, okay, the constraints are the nums dot length belongs to 1 to 25, and the numbers are from -199 to 199. So how should we approach this problem? Let me just clear it again. Now let's suppose we have an array. Let's take a sample array here. 1 minus 2 3 4. Okay. We have 1 minus 2 3 4. Okay. Now how are we doing the splitting? We are splitting this array into some subarrays. Let's say in this case I have split it into two subarrays from indices 1 to 2 and 3 to 4, and we just have to find the maximum possible value. We just have to find the maximum value of cost. Now cost is defined, cost of a subarray is defined as the alternating sums that starts with a plus. If we have to find cost of LR, the subarray L comma R, then the cost will be AL minus AL plus 1 plus AL plus 2 and so on up to AR, right? So this will be the alternating sum, and we have to minimize the sum, maximize the sum. So well, first let us think in a greedy manner. how shall we maximize this sum? So it is very clear to understand that the negative numbers, they should come in negative, and the positive numbers, they should come in positive value. Okay. If this condition is satisfied, we can obtain the maximum possible cost. Okay. But how will we find such a suitable combination such that all the negative numbers are negative in value and all the positive numbers are in positive value? Because these sums are alternating, we'll have to find such a sequence or uh, such a set of sequences such that if we divide the given array into some sub arrays, then that cost that we obtain is optimal. So if we think in a greedy manner, what can we do? Okay, like line colors. Okay. So what if we choose a greedy approach? If we had 1, -2, 3, and 4. The first approach that will strike in our mind is that take this as positive, start with here. Okay, we start with here. Then 2 is coming in negative because this is plus, this will be minus. So 2 is coming in negative, we should take this. Then 3 is coming in positive, we will take it. And then 4 is coming in negative. So since 4 is coming in negative, we will break this subarray here. Sorry. We'll break this subarray here and we'll start a new subarray here again. So again this will be positive. So we have completed our task. The cost is 1 minus -2 plus 3, that is the first subarray, and the second subarray we have 4. So the total sum will be the sum of all the absolute values of all these numbers, that is 10. So this is the maximum possible cost, and we understand that this is the maximum possible cost that we can obtain. So do you think this 3D solution is correct? Do you think this will work out? That whenever we have a negative, suppose we have -3 and we have a positive index coming at it, what can we do? What can we do? Let me just give an example. We have an array. We have, let's say, we have 1, 2, and -3. Okay. So what can we do? We take the positive value here. Okay. Again, this 2 is coming negative value, so we'll start the new array here. Okay. Then we have 1 plus, this is the first subarray here. We'll start the new subarray, so we have +2, and then again we have minus here, so minus of -3. Okay, so this will give us 6. But what if there was just one? Let's say there was just 1 -1 and -3. Okay, so this has a positive value, then this has a negative value. So we'll just take this, and then this will again have a positive value. So even if we start a new subarray here, this will only be a positive value. We cannot make this negative, even if we start the new array here. So we'll continue this array here. Then we'll get the array as 1 minus of -1, and then plus -3. So this value will be sum up to -1. Okay. Now let me just this. Okay. So what can we do here? We have 1 -1 and -3. So if we start here a new subarray, we have +1. Then suppose we make a new subarray here. Even if it's coming in negative, we'll take a new subarray here. So this will become -1 and come with a positive sign, and this will come with a negative sign. So now we'll have minus of -3, and the total sum will be 0 plus 3, that is 3. So you'll pretty much understand that a greedy solution is not work here. Greedy solution would not work here because if you just take the numbers greedily, then you cannot obtain a maximum value. Okay. So what shall be our approach here? Since greedy does not work out, we'll have to try all possible combinations. Like all possible sub-arrays we'll have to try out, and we'll have to find the maximum cost of them all. So with an optimized brute force, this should be a DP solution. DP solution. So how can we approach this? How can we approach this DP solution? Okay, let's start. Okay. So how can we write a DP solution? So the first thing we have to check out while thinking of a DP solution is the constraints. Constraints. So what are the constraints here? Let's take a look again. So the constraints on n here are 1 to 1e5. Sorry. So what can I think about the solution? Uh, we have 1e5 constraint, which means we cannot do n square dp. Definitely we cannot do n square dp. Can we do n log n? Yes, we can do n log n. And what else can we do? Can we do some k times n, where k is not of the order n, like k is some small constant? Yes, we can also do that.
Do just that. So what we can do is that we define a two-state DP. Why? Because I already told you there are two possible states. Either we start a new subarray here or we do not start a new subarray here. There are two ways. So both of these ways we will take. Okay, clarify it further. Um, okay. So let me say we have DP of I of 0. This means that at element, ith element, odd indices are giving are getting negative values. And by odd indices I mean the odd indices are getting the positive values, and by odd indices I mean by one based indexing. I'll show you shortly. Odd indices positive, and similarly dpi of 1 we have this will tell us the maximum possible value if the ith element at the ith element even indices are getting positive values. So suppose we have one based indexing here. We have 1 2 3 4 5 6 and so on. So either we can have this kind of a thing, or we can have this kind of a thing, and so on. So it can be one of these two combinations. That is what I will denote by dpi of 0 and dpi of 1. So the simple solution here would be to either start a new subarray or not start a new subarray. Okay. So we'll make our transitions like this here. dp of I of 0. Now tell me one thing. Uh, let's say the current j is 0. That is, we are calculating dpi of 0. Okay. So in dp of 0, we are assuming that odd indices have positive values. Okay. Okay. Now there arise two cases. I is positive I is odd and I is even. Okay. So as according to one based indexing, we have if I is odd, if I is odd, then it will have positive value, right? And in the next element will have a negative value. In the second case, I is even. This means it will have a negative value, and the next element will have positive value. So like I told you earlier, if we have an even index, suppose, so this index is currently negative, and the next index will be positive. So it does not matter whether we start a new subarray in the next element or not. We'll just continue this, right? There's no point in starting a new subarray right there. So what we'll calculate, this will be equals to the negative of v of I, because the current element will come with a negative sign. So this will be minus of v of I plus plus, and we'll calculate the function. That will be just I plus 1 and j. Right? Why do I write this? Because it's not matter if we start a new subarray in the next element or not. We'll just be adding the uh, with the same hierarchy, that the odd indices will have positive values with the next element. So this will be the sum. But if we are taking an odd element, right, then it will be a positive value. Then next it can be a negative value if we continue according to this, or in the next it can be also a positive value if we start a new subarray, right? So we'll take the maximum. We'll make it v of I. Let me just clear this clutter so I can write it better. Okay. So like I said, dpi 0. This is what I'm calculating. This will have two possible values. I is odd, I even. So if I is odd instances will have positive values and the next one will have negative value. So here in this case we're taking the maximum. This will come with a positive sign because this is odd, and next we'll be having maximum of maximum of dp of I plus 1 of 0 and dp of I plus 1 of 1, right? Because either we can start a new subarray, or we cannot start a new subarray. So if we start a new subarray, then this 0 will become 1, because now all instances will have negative values, so this 0 will become 1. Or if we do not start a new subarray, then this 0 will remain 0. That's how we will be calculating. And if it's even, it does not matter if we start a new subarray or not. So it will be just minus of vi plus dp of I plus 1 and 0. And even in the next case, we make the similar cases. It's very easy now. We have dp of I of 1. In this case, all indices are getting negative values. So in the next, it does not matter if we start a new element or not. And similarly, I is even. In this, even indices are getting positive values, are getting negative values. So in the next, we can choose the maximum out of these. So in this case, we have this dp, right? And in this case, we have this dp. The very same cases. It's basically the same thing with I is equals to 1. I'll just show you the code, you'll understand it better. So here we have a dp function here. first we have taken n equals to num dot size, and we have created a vector of dp of n cross 2, you can see, and initialized its values with long min, and we have found called the dp function. So in dp function, of course, if we have I equals to dp dot size, that's the base case, then we return 0, and if dp ij is not equal to log min, then we return dp ij. These two are base cases we have written, and the next we have just written the two cases that we wrote. First, if j is 0, or first if j is 1, or second if j is 0, right? So if the indices are odd, then we have to take the maximum of this dp of I plus 1 and not j. We just reverse the sign of j, or we do not reverse the sign of j, right? We take the maximum of these, but if I is even, then we just take off minus of pi plus dp of I plus 1 j and v. We did not reverse the sign of j, right? We did not reverse the sign of j. 0 becomes 0 and 1 becomes 1, right? And exactly the same cases are written here, just the conditions are opposite. That if I is odd, then we do not need to take the maximum, we'll just take this condition, you can see right here. And if I is even, then we will take this condition that you can see here, and we'll just call the function, and it will recursively calculate all the values. So that's for C. Now let's come back to D. We have, this is very nice implementation problem. I mean, it's quite a tedious one. You don't want to do it in an interview, but uh, you can learn a bit of implementation from this. That's what I'll say. Or brute force. Let's just clear this first. Okay. So you're given a 2D binary array grid. You need to find three non-overlapping rectangles having non-zero areas with horizontal and vertical sides, such that all the ones in a grid are inside these rectangles. So like I told you, problem B was a subproblem of this problem. So we have to find the three non-overlapping rectangles having non-zero areas, uh, such that all the ones in a grid are inside these three rectangles, okay? And we have to return the minimum possible sum of area of these rectangles, right? Okay. So rectangles are allowed to touch, but they're not allowed to overlap, right? Okay. So just for a sample test case, we'll look at it. We have 101, then we have 111, and you have to choose three rectangles, right? So you can choose one rectangle here, one rectangle here, and one rectangle here. Okay. So earlier when we were doing this problem with one rectangle, we just choose the minimum possible x, maximum possible x, minimum possible y, maximum possible y, and we just took that rectangle, right? Now we have to choose three rectangles. How does this make the problem different? So, well, let us think of a subproblem first. How will you calculate all possible combinations of rectangles, or the minimum possible combination, if I told you that you had to take two rectangles only? Two rectangles only. So this is our grid. This is our grid, n cross n, right? And you want to choose two rectangles such that all the ones are covered, right? Uh, Let me just tell you one more thing. We have the constraints here. So n and m belong to 1 to 30, right? So the constraints are very small. So what can we do here? If you want to choose two rectangles, then obviously we'll divide this whole rectangle into two areas, and you will put one rectangle in both of these areas, right? Either I divide this rectangle like this, somewhere, not necessarily in the middle, anywhere to the left or to the left or to the right. One rectangle will choose in this region, that will cover all the ones in this region, and one rectangle will choose in this region, that will cover all these regions, right? Does not necessarily have to be the whole rectangle, it can be a sub rectangle somewhere around here or around here, does not matter, but it will be in this region. And similarly the other rectangle will be in this region. Okay, any other combination we can choose? Yes, there's one more combination we can choose. We can just simply divide this whole rectangle into two regions, upper region and lower region. So the first rectangle will take in this region, the second rectangle will take in this region. So these are the two possible ways you can do this. uh, think about it a little, you will understand. It's pretty simple logic. We'll just need to divide the whole area into two areas and take the rectangles. Why didn't we divide like this? Because the rectangle sides are horizontal and vertical, that's why. Okay, so this is very clear. If we want to choose two rectangles, we'll divide the whole rectangle into two areas and then we'll try to find the minimum possible combination, right? Now what happens if I tell you to do the same with three rectangles? Three rectangles, three rectangles. So for two rectangles, we did this kind of a division, right? We did this kind of a division, and you're checking all possible rectangles that can cover all the ones in these two areas, right? And we need to calculate the minimum possible area. So if you want to do that, the same with the three rectangles. Can we divide this whole area into three rectangles? So yes, we can divide the same area into three rectangles. We basically divided it into two rectangles, and one of the rectangles we divided into two rectangles again. Okay. So this is 1, 2, and 3. We can divide it into three areas, and we can choose one rectangle in each of the areas, right? Uh, there's any other way? Yes, there's also another way, which is symmetric to this one. We just divide it into two areas like this, and we divide it this way to the left. 1, 2, and 3. We can choose this kind of a combination. What else can we choose? So, like earlier, we divided into two parts from above and below. Similarly, we'll do, and we'll again divide it into two parts. So we have 1, 2, 3. We can take all possible rectangles in these three areas, and we can take the minimum sum. And there's even another way that is symmetrical to the last one. So we have this kind of a division. We have two. Uh, sorry. We'll just divide it this way. 1, 2, 3. We can do it this way also, like we did with this box. Is there any other possible way? Um, I guess there are two possible ways more. Let's look at this kind of a division. Then you can divide the rectangle into three horizontal strips completely, or similarly, we can divide the rectangle into three vertical strips, right? So these are the only six possible ways. You cannot make any other three rectangle division in this whole region. So what we'll have to do basically is we have to brute force and check for all these kind of combinations, right? We just brute force and check for all these kind of combinations. What's the minimum possible area of rectangle we can take? And now this becomes problem B, right? We choose this area, these three areas, and in all these three areas, we choose at least one rectangle. Even if uh, there's there's no one, we choose at least one rectangle. We have because we have to choose one rectangle from each of these three areas, right? So each of these will be a sub problem, like problem B, and for that we will be able to solve by finding a minimum x, maximum x, minimum y, and maximum y, right? So it's just a brute force. We'll keep dividing our rectangles into such areas and check for all possible areas the minimum possible sum of rectangles, where each of these sub rectangles is a sub problem B, and we have to find the minimum possible area, right? So I'll just show you the code, you'll understand. Here's the code here. So I've made a take one rectangle function. That's basically like problem B's. We are given the grid. We have taken the starting x, starting x, starting y, starting x2 and starting y2, and then we have to just iterate through minimum x from minimum x to maximum x and minimum y to maximum y, and we'll just take the minimum x will be minimum of all x, maximum x will be maximum of all x, similarly for min y and max y. And if min x equals to 22 max, that is no one was found in this subarray, we'll return 1 because we have to choose at least one rectangle. And the other case, we'll just return the product like we did with problem B. This is exactly the same with problem B. It's just at the starting and ending indices are given. Okay. And here are the cases. So we have n cross m matrix. So we have the first case, like first case is this one, like I told you. So here if I iterate from 0 to m minus 1, see here we are sweeping this line. Just a second, I'll just add a new one. So in the first case, right, we are sweeping this line. I'll just color it. Okay, so this, okay, okay, so there's this line, we are sweeping it towards the left, towards the right, and there's another line, this line which is sweeping below, right, from above to below. And so we are sweeping this line from left to right. Think of it like this. So what is this line? This is the I line, right? This is the J line, right? This is the column. This is I and this is J. So we are sweeping this J from 0 to M. So similarly we'll sweep from 0 to M, and then we'll go from 0 to n minus 1, right? And then the first rectangle will be the area of this rectangle, right? We have given the constraints from x belongs from 0 to n minus 1 and y belongs from 0 to j. Then from j plus 1 to m minus 1, this whole area, and from j plus 1 to m minus 1 again this area, and we'll make a division that will free from 0 to n minus 1. So this will be the next area. You can see that we have found one rectangle with these constraints. It is very simple. And the minimum area equals to minimum of min area and r1 plus r2 plus r3, the sum of areas of these rectangles. Now coming to the second case, let us look at this. We have the second case. We are here sweeping this line again and this line again. So this time j is just varying from m minus 1 to 0 and I is varying from 0 to n minus 1. So the direction of I is the same, just the direction of j is reversed. So just see, I have reversed the loop here and did the same thing. I've taken a minimum. The third case here, we are sweeping like this, right? This line we are sweeping down and this line sweeping to the right. So I is varying from 0 to n minus 1, like this is sweeping downwards, and j is also varying from 0 to m minus 1. So we are sweeping like this and like this. So right, I is varying from 0 to n minus 1 and j will be varying from 0 to m minus 1. And just taking the three rectangles according to our division. I have also commented the values of x and y. You can just check it for yourself. And you're taking the minimum area, some of these areas, and the minimum area minimum. Similarly, we have the fourth case. It's I think I've not drawn it properly. It's just no, yes, I've drawn it properly. This division is above. Okay. So we have yes. So in this case, this line is sweeping down as before. I is from 0 to n minus 1. Or you can say this line is sweeping from below. That's the way to look at it. It's sweeping up from below, and this is sweeping from left to right. So again, I is sweeping from bottom to up, n minus 1 to 0, and j as usual from 0 to n. So I'm taking these three rectangles, and then the fifth case we have. So we have the fifth case here. Okay. So we have these three rectangles. So we have I sweeping from 0 to n, and again j sweeping also from 0 to n. Both these constraints are sweeping from 0 to n because the y constraints are always from 0 to m minus 1, right? They remain constant. So again, I sweeping from 0 to n, j sweeping from I plus 1 to n, right? And then again we'll sweep from here to here. So I've just taken the three rectangles, 0 to I, 0 to m minus 1, I plus 1 to j, and 0 to m minus 1, and j plus 1 to n minus 1. Just divide these region into three regions, that's all. And the last case here, we have 0 to I will vary from 0 to n minus 1 always, and j will vary from 0 to n minus 1. Like we'll take both the constraints varying from 0 to j, j plus 1 to 0 to I plus 1 to j, minus 1 to j plus 1 to m minus 1, like we did with I. So we have 0 to m, j plus 1 to m, and yeah, from x always vary from 0 to n minus 1, we can see that, and y will keep varying from 0 to I plus 1 to j, and j plus 1 to m minus 1, just like we did with last case. So this is pretty simple, and yeah, we'll take the minimum area and we'll just print the minimum area. I'm just taking the maximum with 3 just in case. I've already included that case in the main function, that it will return at least 1. So this should not be less than 3, but just in case I've taken the maximum with 3 because at minimum we have to take 3 rectangles and their area will be at least 3. So I'm taking the maximum with 3 and return the answer. So this is pretty straightforward brute force, but I will say that you will have to think up of all the cases, so it's not a very good problem to learn. uh, you can learn some brute force, but what you learn about brute force in this, it's just making cases and solving. The constraints are not that high, so it does not matter. uh, so yeah, that was Leetcode Weekly 403. Stay tuned in for the next contest. Thank you.